A technique that builds on the same core idea as divide and conquer is dynamic programming. Let's take a closer look at it. Like with divide and conquer, let this box represent a large and complex problem. Dynamic programming also exploits the property that some problems can be divided into smaller subproblems that can be solved individually. However, if the subproblems are not completely separated, but overlaps, the overlapping part would need to be solved in both subproblems. In a recursion, we could end up with overlapping parts that are shared among a huge amount of subproblems, leading to a vast amount of repeated work. In dynamic programming, the subproblems, including the overlapping parts, are solved only once, and the result is then stored in a cache for reuse. With a cache of sub-solutions in hand, dynamic programming combines the sub-solutions just like divide and conquer, and in that way ends up with a solution to the original problem, but without having to solve the overlapping parts repeatedly. Recall the recursive Fibonacci implementation from Module 2. Also recall the Fibonacci sequence, where I have printed the first few entries here. Here is the execution graph, illustrating how the recursion progresses with an input value of 5, starting with Fibonacci of 5 as the initial call, and then that call dissolves into calls with smaller and smaller input values. Notice how many times, for example, Fibonacci of 1 is called. 1, 2, 3, 4, 5 times. If we did the same exercise for a larger input value, say 30, Fibonacci of 0 would have been called 514,000 times, and Fibonacci of 1 would have been called 832,000 times, and so on. That's an explosion of identical subproblems, and you may now see why the execution time explodes similarly. We will fix that problem in a moment, but first I would like to show you a small fun property. Here is a table illustrating how many times the Fibonacci function is called with different input values named n when the initial input value is 20. I have split the table into two because the full table couldn't fit on the screen. Notice the count column, which states how many times the Fibonacci function is called for each value of n. If you read it bottom up, you can see that it is the Fibonacci sequence itself. Isn't it interesting that the number of calls of each recursion step of the Fibonacci function is a Fibonacci sequence itself? Well, let's go introduce the cache and fix the subproblem explosion. Our goal is to be able to execute Fibonacci of 80, which was impossible in the original implementation. So here's the Fibonacci function as we know it. Let me first try to execute it with the input parameter of 8. Fibonacci of 8 is 34, okay. That went relatively quickly. Let me try with 20 to see if we can do that. 20 also went pretty fast. Let me try 40. That went relatively fast. The output number is pretty large. I think I can handle Fibonacci of 80. Let me run that. It seems to take a while. Let me pause the recording and get back once it has completed. I think I give up. Take a look at how many hours it has been crunching. Let us try the dynamic programming version instead. So now I have introduced a cache with the length of 200 longs, and in the implementation I will now use the cache where possible. So for n smaller than or equals to 1, then the cache should just be initialized to 1. Otherwise, if there is no cache for a given input value, then that cache element should be set to the corresponding recursion step. Notice that this is only done once. In all subsequent calls, this cache element has been initialized, and then we will just use that when we return from the function in the last line. Let us try to execute Fibonacci of 80 once again. That went fast. and the output value was quite large. Let us try with 100 instead. That wasn't a problem either. So in this rather simple case, it was obvious that the dynamic programming approach using a cache had a significant influence on performance. We can utilize the cache in two ways. The strategy we just saw with the Fibonacci method was a top-down strategy, where the cache was filled on the fly as the recursion progressed, and the final solution was built on the way back up the recursion chain. Another way of using the cache is a bottom-up strategy, where the complete cache is constructed in a phase 1 and the solution is built in a phase 2. Let's consider a few problems where this bottom-up technique is useful. One example is a setting with a server with a certain capacity and a bunch of virtual machines that uses different amounts of resources and that has a certain value, for example a price or a priority. The challenge is now to pick the set of virtual machines that would maximize the value so that the total sum of resources used by the chosen virtual machines still fits within the server's capacity. Another but similar problem is to choose a selection of batch jobs to run within a certain time limit in a setting where each batch job comes with a value, for example a priority, and an expected execution time. Last, we could consider a pool of investment candidates where each possible investment has a price and a potential. The problem is now to choose the set of investments that maximizes the combined potential while still being within our allowed budget. The aforementioned problems are all special cases of the so-called 0-1 knapsack problem, which can be described as follows. We are given a basket or a bag or a knapsack with a certain capacity, say 4 pounds, kilos, or some other unit. We also have a bunch of items. Each item has a weight and a value. The problem is now to choose the set of items that would maximize the total value while still fitting within the knapsack's capacity when considering their weight. Each item can be included either 0 or 1 times, thereby the name of the problem. If we did it the brute force way, each item can either be included or excluded from our final selection. That is 2 possible options for each item, or 2 times 2 times 2, which is 8 possible solutions when considering all items. For 3 items that's definitely a manageable problem size, but when the number of items increases, the number of combinations explodes, and so will the execution time of the brute force strategy. Let's try to solve the problem using dynamic programming instead. The first thing to figure out is how to divide the large problem of considering all the provided items into a knapsack with a full capacity into smaller sub-problems. One thing we could do is to consider the case of a knapsack with 0 capacity, then a knapsack with capacity 1, and so on until we reach the full capacity, which in our case is 4. We could also consider the case of including none of the items, the case of just considering one of the items, the case of considering only 2 of the items, and so on until we reach the full case of considering all the provided items. This gives us a table representing all the subproblem combinations we just talked about. At each table cell, we can write the maximum possible value for the corresponding subproblem. In order to be able to refer to the items with a number, I associate them with an integer variable with the values 0, 1, 2, and 3 for the 4 options. We will represent the table with a 2-dimensional array, M, where the first We will represent the table in a 2-dimensional array, M, where the first dimension specifies the table row and the second dimension We will represent the table in a 2-dimensional array, M, where the first index specifies the table row and the second index specifies the table column. The number of rows is 1 larger than the number of items, since we also consider the case with no items. And the number of columns is 1 larger than the knapsack capacity, since we also consider the case with 0 capacity. Let us start filling out the cells that comes for free. For example, the leftmost column representing the subproblem where the knapsack has a capacity of 0. In this case, no items will fit in the knapsack, so the maximum possible value in all cases is 0. Similarly, we can consider the subproblem represented in the top row, where we have no items to put in the knapsack. In this case, the maximum possible value is also 0, because with no items, we have no value. Now the fun begins. Hold tight. Let's start from the top left empty cell and move down towards the bottom right cell, which represents the full and original problem. In this case, we will solve the subproblem of only considering the first item, the flashlight, in a knapsack with a capacity of 1. The solution to that subproblem will be stored in M with row or index I equals 1 and the column or the capacity variable equals 1, 2. There are two cases. Either we exclude the corresponding item from the final solution, or if the item fits the knapsack capacity, we will include it in the final solution. If we do not include the item, then the maximum possible value we can obtain is already solved, because that can be found in the row above. Here I have drawn a red circle around that case. So if we choose to not include the flashlight, then the maximum value of our solution is the answer to the subproblem where we did not consider any items. If the item does fit in the knapsack and we do include it, then the total value of the knapsack would be given by the value of that item, shown here in the green circle. But after adding the item, there may be room for something more. How much more? Well, so much that can fit in a knapsack with a capacity subtracted the weight of the currently added item. We can find that value in our M array for the subproblem where we do not include the current item, because we have already added it, and subtract the item's weight from the capacity of the knapsack. The maximum possible value of the current subproblem must be the maximum of these two possible situations. So, a whole lot of talking, but now the basic algorithm is in place. In this specific case, the answer is easy, because the flashlight with a weight of 2 does not fit in the knapsack with a capacity of 1, which is the subproblem that we are considering now. So, the maximum possible value for that subproblem is 0, and we do not include the flashlight, which I will note with a red cross. In the next subproblem, we will still only consider the flashlight, but now the capacity of the knapsack is 2. Again, there are two options. Either we do not include the flashlight, in which case the maximum possible value can be found in the row above, or we do include the flashlight, in which case the maximum possible value is the value of the flashlight, which is 2, plus the value we can obtain with the flashlight cut from the solution. And that latter value can be found in the row above in the column 2 positions to the left, because the flashlight had a weight of 2. So the value of 3 plus the value of 0 from the cell marked with the green circle gives a total value of 3, which is larger than the value of 0 from the red circle. So we fill our current cell with 3 and mark that this subsolution does include the flashlight. The rest of that row represents the subproblems with even larger knapsacks, but since we do not include any new items, the subsolutions must be the same for the two remaining columns. So, now consider one more item, namely the book. So the subproblem we consider now concerns the flashlight and the book, and with a knapsack capacity of 1. If we do not include the book, the solution is given in the table cell above. We cannot include the book because it has a weight of 2 and the knapsack capacity of this subproblem is only 1. So the maximum possible value is 0 and we do not include the book. In the next subproblem, the knapsack capacity is 2. As before, we have two options. Either we do not include the book, in which case the solution value can be seen in the row above, or we do include the book, in which case we get a value of 1 from the book itself, plus the value found in the subproblem where we subtract the book's weight from the knapsack capacity, because we have already used that capacity for the book. That subproblem is marked with the green circle, and in this case its value is 0. The maximum value of these two cases is 3, which comes from the red circle, but in that case we did not include the book. We fill out the M-array accordingly and proceed to the next subproblem. Here the knapsack capacity is 3. Either we do not include the book, in which case the maximum value can be found in the row above, or the book is included, in which case the total value is the book's value of 1 plus the value obtained from the remaining capacity, in this case 0. Again, the largest value is 3, which comes from the row above. So we write 3 in the array and mark that we do not include the book. Next subproblem is with the full knapsack capacity of 4. Either we do not include the book, in which case the maximum possible value is found in the row above, or we do include the book, in which case the total value is given by the book's value of 1 plus the maximum possible value in the subproblem with the knapsack capacity subtracted the book's weight of 2. In this case that value is 3, resulting in a total value of 4. So here the case where we do include the book results in the largest value. So we write 4 in the table and mark that we do include the book. The last row represents the subproblems where we also consider the pencil. We start with the subproblem where the knapsack capacity is 1. Either we do not include the pencil, in which case the maximum possible value can be found in the problem solved above, or we do include the pencil, which has a weight of only 1, and in this case we would have the pencil's value of 3 plus the maximum possible value of the remaining capacity. The maximum of these two cases is 3, so we write that and mark that we do include the book. The next subproblem has a knapsack capacity of 2. Two cases. Either we do not include the pencil, in which case the maximum possible value can be found in the subproblem solved above, or we do include the pencil, in which case we obtain the pencil's value of 3 plus the value found for the subproblem with the pencil's weight subtracted. In this case the value is 0, so the total sum is 3, just like we got 3 as the maximum value for the case where we did not include the pencil. Both choices will end up with the same maximum value. Let's write 3 in the table and let's choose to include the pencil. We are almost there. The next subproblem has a knapsack capacity of 3. Either we do not include the pencil, in which case the maximum possible value can be found in the subproblem above that we have already solved, or we do include the pencil, in which case the maximum value is the pencil's value of 3 plus the value obtained from the subproblem with the pencil's weight of 1 subtracted. In this case that subproblem had a maximum value of 3, so the pencil's value of 3 plus the subproblem's solution value of 3 gives 6. This is the largest of the two options, so we write 6 as the maximum possible value and mark that we do include the pencil. The next and final subproblem has a knapsack capacity of 4. Either we do not include the pencil, in which case the maximum possible value can be found in the subproblem in the row above. In this case we can obtain a value of 4. Or we do include the pencil, in which case the pencil's value of 3 should be added to the subproblem with the pencil's weight of 1 subtracted. Also, this subproblem has a maximum value of 3, and added to the pencil's value of 3, we again obtain a total of 6. We choose that over the solution with value 4 from the red circle, and conclude this table filling by writing 6 in the last cell and mark that we do include the pencil in this case. So, done. Let's clean up a bit. What have we achieved now? We have found the maximum possible value that can be obtained by picking one or more items into our knapsack for varying capacities and for increasing subsets of items. The answer to our original problem with a capacity of 4 and with all items considered can be found in the lower right corner. The maximum possible value for our original problem is 6, but what items are included in order to achieve that value? This can be deduced by looking at the crosses and the check marks. Let's get rid of all the noise that's no longer necessary. By the way, in the real life, we could implement the value table and the included-excluded table in 2 arrays. So, in the lower right corner, we can see that the pencil is included in that largest of all the subproblems. When the pencil is selected, we have no use for the corresponding row anymore. Also, in order to see what should be included in the remaining knapsack capacity, we should look at the subproblem where the pencil's weight is subtracted. That can be found here. In this subproblem, the maximum value is obtained by not including the book. So we will skip the book and look at the even smaller subproblem straight above, because the knapsack capacity hasn't changed since we added the pencil. In this subproblem, the flashlight is included. We include the flashlight and have now investigated all the items. So, by putting a flashlight and a pencil in the knapsack and leave the book out, we obtain the maximum possible value. But what is the complexity of finding a solution? Assume that there's n items and that the capacity of the knapsack is C. As we saw before, investigating all possible configurations had a complexity in the order of big theta of 2 to the n, which is an exponential function which explodes when n grows. In comparison, the dynamic programming approach was a matter of filling out the table, which size was big theta of n times c. So the dynamic programming approach is significantly faster. However, we pay with a space requirement for the table. A quick cliffhanger comment. There's a minor twist on this n times c complexity. But I will come to that in the next module, where we will talk about computationally hard problems. I have included an implementation of the 0-1 knapsack problem that we just solved in the source code that comes with the course. Dynamic programming can be used to solve a vast amount of problems. For example, it can be used to decide where to put line breaks in a text in order to obtain a nice and even text justification. The main observation here is that the position of the line break in one line influences where to put the line breaks in the remaining lines. Dynamic programming can also be used to construct optimal routes in a network. The by many programmers heavily used diff command uses dynamic programming to deduce the difference between 2 text files. Dynamic programming can also be used to match DNA sequences efficiently. Given a subsequence of a DNA string, the best possible alignment can be deduced, and by comparing the possible alignment quality among DNA from different animals, it can be seen from which animal a given DNA sequence must come from, even without having an exact match. And as a last example, dynamic programming can be used to find optimal strategies for games such as Tetris, Super Mario, and Blackjack.